Good morning, ladies and gentlemen. We are going to start the countdown on time. Welcome to the late breaking news session. This morning we have indeed late breaking news with feedback and current status of the Prisma mission. This presentation will be presented to us by Mathias Persson. He is the current CEO of ECAPS. He completed a degree in aeronautical engineering and fluid mechanics. He worked for the Aeronautical Research Institute. There's been a few name changes. It's now part of the Swedish Defense Research Agency. For several years he was in the IT industry as CEO, while he continued with consulting on computational fluid dynamics. And since 2007, he's been full-time at ECAPS. And since January of this year, he's been appointed as the CEO of ECAPS. And he will talk to us about the on-orbit demonstration of the Prisma mission. Thank you, Mathias.
Ladies and gentlemen, good morning. I'm happy to see so many people here this last morning. It's always a challenge to attract interest to the audience the very last day. I'm the president of ECAPS, and ECAPS is a subsidiary to Swedish Space Corporation. And we are focused on green propulsion. We are working with a novel technology. We name it High Performance Green Propulsion, HPGP. And I will give you first an outline of this technology, the objectives of both the Prisma mission and the objectives for ECAPS on flying on this one, and discuss the on-orbit validation that we have done so far, and some conclusions at the end. So please, if you have questions, save those to the end of the session, and I will answer them. So, green propulsion. In 1995, Swedish Space Corporation initiated a pre-study about green propulsion. Due to the scientific needs for a more versatile way of propel our satellites, the scientific community wanted to have liquid propulsion, and since hydrogen is since 40 years the main way to do this, especially for small satellites, monopropulsion hydrogen, and that's related with a lot of risk and hazards and a lot of cost. We started to develop or do research about green propulsion, and we investigated a lot of different oxidizers for this technology. And in '97, we formulated this technology based on ADN, ammonium dinitramide, as an oxidizer. That's an energetic salt, which is in a solution with water, and we add methanol as the propellant, or fuel actually, and we have ammonia as a stabilizer to this. And this is the patent ECAPS have on the propellant itself and the blends. It combusts at a very high temperature. It's 1600 degrees Celsius, which means that we had to invent a high temperature resistant catalyst and a thrust chamber assembly to withstand these temperatures. The ADN-based monopropellant offers high performance, reduced hazards, and overall lower mission costs. We'll come back to that later. And it's also the first high-performance green propellant qualified for spaceflight. Here you see the color of the propellant. It's a bit like white wine, actually. It's kind of nice looking and very easy to handle. Okay, performance-wise, we have a specific impulse which is 6% higher than for monopropellant hydrogen. And since the density of the propellant is 24% higher, we gain 30% more efficiency regarding density-specific impulse. Here you can see the curves for ISP versus feed pressure for our 1 Newton thruster. The left curve is the ISP, and the right curve is the density-specific ISP. So you see the significant increase. Oh, sorry, the pointer is not working, but anyway, to the right you see the significant increase in density-specific ISP. So, environmental hazards. Hydrazine is highly toxic, it's carcinogenic, and it's sensitive. While we have a very high energy content propellant, which is low sensitive, it's very low toxicity, and it's non-carcinogenic. And it's also biodegradable. If you pour that out on the soil, it will actually turn into a fertilizer by the UV radiation of the sun. Expensive fertilizer though, but anyway. This gives us real benefits when loading a spacecraft, for instance. We will see more about that later. More about the characteristics. The specification is set equal as for hydrazine, plus 10 to 50 degrees Celsius. However, we have performed firings with the propellant inlet temperature below zero, down to -5 degrees Celsius and up to 60 degrees Celsius. Long-term storability is -7 to, with the nominal temperature is storable for more than 20 years. But we can, in short term, store it below zero to -7 and up to 120 degrees for short period of time. At -7, it starts to saturate, starting to develop. It may develop crystals in the propellant. However, they will be resolved again when the temperature is raised. And at -90 degrees, it will become a solid, but it will not expand. So if you put it in a glass jar and freeze it down to -90 degrees, the glass jar will not break. And this is kind of interesting, give you new interesting perspectives of signing new kinds of missions. We haven't done demonstrations on that yet in space, but we really hope to be able to do that in future. Okay, so the Prisma mission objectives. Prisma is the test bench for our propellant and propulsion system. Prisma is a formation flying mission with rendezvous and close proximity operations. We test different sensors on the platform. And we have 2 satellites now in low Earth orbit. The main satellite, called Mango, has a propulsion system, or actually 3 propulsion systems on board. And the target, Tango, is a passive satellite. The weight of Tango is 45 kilograms and Mango is 150. These are the Prisma partners, Swedish Space Corporation, DLR, CNES, DTU, ECAPS, and Nanospace. Well, actually there are more, but these are the prime partners anyway. And we are providing the propulsion system, the green propulsion system. So ECAPS has also its objectives with the Prisma flight. First of all, we will have the benefit of have this as a platform to test high-performance green propulsion in space in order to show the maturity of this technology. Secondly, we will provide Delta V to the Prisma mission. And third, we will also act as a backup to the hydrazine system that's also on board. These are the 3 propulsion systems that we have. The hydrazine system in red, the HPGP in green, and a small it's a micro-propulsion system that's seen there to the right too. We have 6 thrusters, hydrazine thrusters, and 2 HPGP thrusters on board. Thanks. So the hydrazine system gives 120 meters per second delta V, and the green propulsion system gives us 60 meters per second delta V with 5.5 kilograms of propellant. Here is the hydraulic schematic of the HPGP system, and the interesting part here is that essentially we use commercials off the shelf used for hydrazine normally. The only novel part in this system is the propellant itself, and the thrusters. Stainless steel tubing and valves used for hydrazine is used in our technology demonstration as well. Here's the thruster to the left and the HPGP system on the mounting plate to the right. We launched the satellite from Yasny in Russia. And in order to get there, we flew all the equipment, the ground support equipment, the satellites, and the propellant on the same aircraft cargo plane. We've also flown the propellant with a passenger plane from Stockholm to Kiruna. And this is due to the fact that the propellant is classified as in UN class 1.4S, which allows air cargo transportation. We can ship 50 kilograms on a commercial airliner. Okay, regarding loading of propellant. The Russian launch authorities in Yasny declared this as a non-dangerous operation. Everyone knows that fueling with hydrazine is a dangerous operation and special measures has to be taken care of. We didn't, or we don't need to use escape operations in order to load the propellant. And it's not sensitive to exposure to air or humidity, which is making life easier if you have to decontaminate and refuel the satellite. The loading cart after fueling was very easily cleaned out, and I will come to that later. This is the launch campaign for us doing the loading. You can see here it's the HPGP loading was conducted over 7 days with a crew of 3 technicians. And the hydrazine loading took 14 days with a crew of seven experts. We bought that service. We didn't load hydrazine ourselves, but we supervised that operation. And this is a significant saving in time and effort. Also, the launch base had to provide support from their experts, medical help. They had the scrubbers and the rescue teams and all that in ready during the hydrazine fueling. And of course, no one could work on in the facility at the same time the fueling was ongoing. While we had the possibility to continue with checkouts and didn't have to evacuate the facility while loading HPGP. The whole campaign took 20 days, and that's really amazing. We flew out from Stockholm, or sorry, from Örebro, May 17th, and yeah, that's kind of a very condensed and rapid launch campaign, I would say. So this is how it looked like when we're loading the propellant. Here you see the crew working with hydrazine. They have to use escape suits, and with the backup team, of course, in the next, be ready if something happens. While we could work in clean room smokes, it's just splash protection, and it's regular clean room suits actually. And as you can see, we can work on a computer while loading the propellant. There is not special taking care of any electrical device or so. No breathing help or something like that. You actually see a bottle of water there too. That's kind of an amazing thing. I don't know if they, I mean, they're working for a couple of hours, so you have to drink sometimes, and I don't think you drink without any escape suits while loading hydrazine. So this is a transfer tank and the fuel loading cartridge that we used. The toxic waste for cleaning out the cartridge was 470 kilograms for the hydrazine fueling cart, while we produced 3 kilograms of non-toxic waste. And well, the propellant waste, or the extra propellant that we had to buy hydrazine, the 29 kilograms that were left over, had to be destructed by the launch base, not free of charge, of course. while we had 1 kilogram left, and extra additional propellant that we didn't use, we shipped that back on the truck together with the ground support equipment. The propellant waste was taken care of free of charge by the launch base. Actually, they just burned it together with a package we sent the propellant in. So it's very easy to get rid of. So this is the satellites, the target satellites on top of the Prisma main satellite. And here you see some of the assembly in the, to the space head and the rocket in this silo prior to launch. We launched together with the French satellite Picard. As you can see on this sketch, the Picard was on top of the Prisma satellites. And that's also something to consider. When we loaded the HPGP, they could still work with the Picard satellite, while during hydrogen fueling everyone left the base. So there's significant costs also to be saved for that kind of activities. So on June 15, we had the successful launch with the Dnepr. And on June 24th, we had the first firing of HPGP in space. And this was exactly 11 years after the first, very first demonstration thruster was fired in south of Stockholm. So 11 years of R&D from the first experimental thruster to we had the first firing in space. And everything went nominal. We have some interesting features on the Prisma satellite. Since it's oriented to the sun, we have one side which is hot and one side which is cold. And that's very interesting for us, since we have one thruster on the hot side, on the sun side, and one on the black side. And that gives us a lot of important information regarding this technology integrated on the spacecraft. After commissioning the system and the separation from the target from the main, we had the first dedicated HPGP session. It's called HPGP1. And this is actually a session where we can perform our own experiments in space in order to assess the performance, to compare that with the hydrogen system, and to do ECAPS experiments. Otherwise, the HPGP system will work in a combined mode together with the hydrogen system. So actually the spacecraft will decide which thruster to fire in order to get the best delta V out of the propellant. And that's kind of a unique feature, I would say. And so we know after each lap, or when we have contact with the satellite, what have really happened. So the system is really working as an important primary propulsion system on board together with the hydrogen system. Later this year we will conduct more dedicated sessions regarding performance mapping, and at the end of the mission we will have the opportunity to burn more of the propellant. So we will continue to work with this during the whole Prisma mission. However, we have already, during this early harvest, gained a lot of interesting data, which I will show you now. This is actually flight data. You can see here is the tank measured pressure. That's the red dots here. And due to the fact that we have different temperature when we measure the pressure, we have to normalize it. And that's the green rings you see here. And straight line here is the tank normalized pressure. Let's see here. Sorry, the red ones was the temperature and the green one was the pressure, and then we normalize it to get the line. And you see how the propellant and the pressure is dropping. That means the propellant is consumed. And this is the propellant mass gauging. We have to calculate backwards in order to see how much propellant do we have left. And this is actually the mapping then for different pulses that we have performed. And it used to be non-filled rings here all over the place, but since when we have a black dot, that means that we have a hot firing that is actually confirming the predicted or planned pulse. And for all these pulses, we have gained information that everything is nominal. And I would say that these are, you can see here is a long firings. This is a duty factor, and this is a T on time. So I mean, if you have a very low duty factor and a long T on time, that means you have a long firing. This is the minimum impulse or the impulse bit, and this is ground test data. The straight lines here is the ground tested data at different pressures, and the blue dots are hot firing data from space. And the repeatability is within plus minus 2.5%, which is excellent, actually. And compare with the hydrogen system that we have on board, you can see here different pulses fired. We have assessed that we have the 6% gain in ISP as we claimed to have from the beginning, and that was expected. And the HPGP is actually verified in its performance for all these pulses that has been fired. And that's really an achievement, I would say, for the first dedicated HPGP session. So we have done the onboard validation for HPGP onboard Prisma. The performance is repeatable, it's predictable, and it's verified. And it's better than hydrazine, and that's really a goal that we have been looking for a long time now, to actually demonstrate this on space. And now we've done it. So conclusions. Well, in space functionality and performance of the HPGP propulsion system is being verified, and it's the launch campaign savings is significant, 1/3 of the cost compared to fueling with hydrazine. So we have both demonstrated the low hazardous benefits of using green propulsion, and we have demonstrated the higher capacity or higher performance in space. The Prisma mission will continue, as I said, doing all its formation flying experiments. Here you can see different orbits for the main satellite relative to the target, and the HPGP system is used for that. It's used together with the hydrazine system. And actually it's less propellant consumed than we expected. So after the complete mission, it will be a lot of delta V left. And this is a unique opportunity for scientific community, which can actually come to Swedish Space Corporation and perform their own formation flying experiments with their own algorithms. So that is something that we promote now, and you're very welcome to get some more information about that. Here I have some brochures with me, and we are also on this exhibition, and will happily talk to all of you that have an interest in formation flying. So I would say thank you for listening, and I'm open for questions.
All right, good effort there. Are you receiving interest from larger satellites, not just small satellites? And can you talk about the feedback that you've gotten from companies that build satellites?
You mean interest in this formation flying capability?
Well, in
Oh, okay, yeah, that's correct. We have had a lot of interest regarding this technology, and I would say that both we and the community has been waiting for some real flight data, and now it's really getting momentum again. And this technology is actually considered for a lot of different kinds of missions. Small satellites, of course, benefit from the increased density-specific impulse, while larger ones also do that. I mean, they could continue or prolong the mission, or they can actually make the satellite a bit smaller if needed. And yes, we have been offering systems for 150 to 200 kilograms of propellant. I mean, it's not tons of propellant, so I would say it's not the largest satellites that we have approached yet. Those are still looking for biprop. But if we do a trade-off, propulsion system of about 280 kilograms, we are actually competitive to a biprop system with this technology. Since you have, on the biprop you need to have double tanks and a lot of pipings and pressure regulations and so on. So we can actually compete on performance for a system that is up to 280 kilograms wet mass. More questions?
I have one question. We have only seen the benefits of this propellant in comparison to hydrazine. What are the downsides?
Yes, there must be a downside, of course. And I would say the downsides we have is that we need to preheat the catalyst bed before firing. So we heat it to up to 300 degrees and then we can fire. However, you have to preheat the catalyst bed on a hydrazine thruster as well. Otherwise, you will ruin the catalyst. So there is we cannot cold start from complete cold. While in hydrazine thruster you can do that, but you will ruin the thruster after a few attempts. So, but that might be a drawback. And then, of course, that's the heritage. We have to get this message out and get the community to look into this and to consider this for their missions. And the drawback is that we have a lot of heritage to compete against, I would say. But otherwise, it's extremely promising. And this low hazardous approach open up new way of thinking for missions. For instance, you could consider preloaded satellites or tanks that are loaded before integrated into the mission or spacecraft, and then pressurized and then launched. That would be enormously important for responsiveness. And you could, for instance, have a system up in space which is in a sleep mode. Maybe it's sort of deep frozen, or maybe kept at a very low temperature anyway, and then you can wake it up and start the mission. There is other benefits with the propellant, that we can mix the blend in the way that we have even lower temperature that that we can operate the thruster, and that we don't get saturation. For instance, if we go below 20 degrees below zero or 40 degrees, that would gain a lot when talking about monopropulsion system close to cryo stages, for instance, or for deep space missions. So there are huge potential in this, and we have just started, I would say.
Are there more questions?
Okay, thank you.
Okay. Thank you to the speaker. I think 40 years from now, people will start proposing a new propellant after this one has taken hold as the dominant propellant. Thank you very much, Mathias.